To prove that the set of best responses is equal to the set of undominated strategies, we're going to use a result called Farkas' lemma. It says that if you have a matrix, an m by n matrix, A, and you have some vector B, so an m-dimensional vector, B, then either you can find some vector x such that when you multiply the matrix A with x, the result is less than or equal to B, or you can find an m-dimensional vector y such that when you multiply y times A, that's a positive vector, and when you multiply y times B, the product is less than 0. So this is going to be the dot product of these two. I'm sure at this point you're wondering what you've gotten yourself into, and you're thinking, where's the game theory here? But I'm going to show you how we can use this lemma to prove our result. Given some SI, we're going to construct an A and a B, and once we have the A and the B, either we have an X or we have a Y that satisfy these conditions. If we have the X, I'm going to show you that that X can be translated into a mixed strategy that dominates SI. If we have a Y, I'll show you how to use that Y to create a belief such that SI is a best response to the belief that we create using Y. By Farkas' lemma, either there's the X, so that S is dominated, or there's a Y, so that X is a best response to some belief. So it's one or the other. So any given strategy is either dominated or it's the best response, which means that the set of undominated strategies and the set of best responses have to be the same. Let's go ahead and start the proof of the proposition now, and we're going to appeal to Farkas' lemma in that proof. So let's say you have some strategy SI, so let SI be some strategy for player I. What we're going to show is that this strategy either has to be dominated or it has to be a best response to some belief. So we're going to define this matrix A. Remember, A is an m by n matrix, so it's going to have m rows and n columns. M, recall, is the number of profiles of other strategies. N is the number of strategies that I has. So the number of columns is the number of strategies that I has. Each entry in this matrix, so if we look at the LK entry, is the difference between the utility you get from playing strategy SI and playing strategy SIK. So you either play strategy SI, so the strategy that we started with, or the kth strategy, when we've enumerated all the strategies. And you look at the utility difference that you get when everybody else is playing the Lth strategy profile. So for every K and L, we're going to do this, and that's going to give us this whole matrix A. So in the left top corner here, we've got the utility difference between playing SI and playing SI1, so the first strategy for player 1, when everybody else plays the first strategy profile. Along this row, we keep the strategy profile for everybody else, but we just change the strategy that we're comparing SI to. We look at the utility difference between playing SI, and the last column is going to be the nth strategy for player I. So we start with the first one here, the second one, third one, fourth one, we keep going until we get to the nth one. The columns, let's again look at the first column. We look at the difference between playing SI and SI1 when everybody else plays the first strategy profile. Then we look at the difference between SI and SI1 when everybody plays the second strategy profile, and so forth until we get to the difference between SI and SI1 when everybody plays the mth strategy profile. So we do this for every combination of alternative strategies SIK for player I and strategy profile of everybody else S minus IL. Let B be just a vector of -1. Remember, B is going to be an m-dimensional vector. So m-dimensional vector of -1s. So by Farkas' lemma, there's two possible things that can happen. Case one, there exists some x, and this x is greater than or equal to 0. X, remember, is going to be an n-dimensional vector. And if it's greater than or equal to 0, it means that every component of x is non-negative, such that ax is less than or equal to b. So if we multiply this matrix A times x, we get a vector of numbers that are all less than -1. The second case is there's a y. Again, y is going to be, in this case, a m-dimensional vector, and y is going to be a vector of non-negative numbers, such that ya is non-negative and yb is strictly less than 0. Farkas' lemma tells us that only one of these two could be true. In the first case, I'm going to show you how you can use x to create a strategy that dominates Si. In the second case, I'll show you how you can use y to create a belief such that Si is a best response to that belief. Again, just to reiterate, Farkas' lemma says that exactly one of these two cases holds. Both can't hold, but one of them holds. So let's see what to do in case 1. If case 1, now we don't know if x itself is an element of the set of probability distributions over Si. In other words, we don't know if x is a probability distribution over Si. Why might it not be a probability distribution over Si? Well, it might be that if you add up the components of x, they might sum to greater than 1. One thing you know for sure here is that x is non-negative. So all the elements, so you have some vector x. So you have x of Si1, x of Si2, and so forth, all the way to x of Sin. Now, all of these have to be greater than or equal to 0. Moreover, at least one of them has to be positive. Why? Because if you take the product ax less than or equal to b, then b is all -1s. So if a times x is less than or equal to -1, x can't possibly be all zeros. So at least one of these x's, one of these things has to be non-zero. However, we don't know if we add these things up, do we get 1? Not necessarily. We might get something greater than or less than 1. And that's why x might not be a probability distribution itself. However, since all of these things are non-negative, if we take the sum of them, this thing here, let's call that capital X, and we divide each of these by capital X, then what you end up with does sum to 1. Because if we add these up, then we get x divided by x, and that's equal to 1. And all of these are non-negative, so they're all between 0 and 1. So this thing is a probability distribution over Si. And that's exactly what we've defined as being sigma I. So sigma I is just x divided by the sum of the components of x. I'm going to claim that sigma dominates Si. So why does sigma dominate Si? Let's look at this product. If we take one of these rows and multiply it with x, we know that that has to be less than or equal to -1. So if we write that out, we see that the utility difference between playing Si and Si1 when others play S minus I1 times the first component of x plus, we keep doing this, the utility from playing Si minus the utility from playing the kth strategy when everybody else plays S minus I1 times the kth component of x all the way through. We keep adding until we get to the last term, which is the utility difference from playing Si versus the nth strategy when everybody else plays the first strategy profile times the last component of x. If we add this all up, that has to be less than or equal to -1. Of course, that's true for every row, even for the last row, which is what this says. So no matter what others play, the utility difference from playing SI versus the kth strategy times the kth component of x, if we add those up over all k, we get something that's less than or equal to -1. What you can do now is just to divide this whole thing by capital X, what we called capital X, which was this thing. You can write out the lth row, or the lth inequality, and it becomes the following. So we can factor out here the ui of SI when everybody else plays the lth strategy profile. So we just end up with that times the sum of xi's, and we're dividing through by capital X, minus, so this part, the sum of UI, the utilities that you get from playing the kth strategy, summing over k, times x of SIK divided by capital X. That has to be less than or equal to -1 over x. Remember, x is a non-negative number, so -1 over x is a negative number. This guy right here is just sigma. This thing is just 1. So we get that the utility difference between playing strategy SI, or this is nothing but the expected utility from playing sigma I. Remember, this thing is just sigma I. And that's a negative number. So the utility difference between playing SI and the mixed strategy sigma I is negative. And this is true for every L. For every single row, we have this strict inequality, which means that the utility from playing sigma is strictly higher than the utility from playing SI for every possible strategy that the others could play. Thus, sigma I dominates SI. Now we'll turn to the second case, where there's a Y, where Y times A is non-negative and Y times B is negative. Just like the first case, we're going to normalize Y. So this exercise of dividing Y by the sum of the components of Y is called a normalization. So we're going to divide Y by the sum of the components of Y to define theta minus I. So this is going to be the belief for player I, and we're going to show that SI is going to have to be a best response to this belief. Since Y times B is less than 0, Y cannot be all zeros. So we're not doing a divide by 0 here. If we look at the system of inequalities, Y times A greater than or equal to 0, and we write out the kth inequality in that system, we have that if we take the sum from L equals 1 through M of Ui of Si S minus IL times theta minus I S minus IL, and we subtract from that the same expression except replacing Si with Sik, that difference is greater than or equal to 0. The first term is nothing but the expected utility from playing Si given the belief theta minus I. The second term is the utility from playing Sik given the belief theta minus I. Since the difference is positive, the first term has to be at least as big as the second term. So this says Si gives you at least as high a payoff in expectation as Sik given your belief theta minus I. Since this is true for every k, Si has to be a best response to theta minus I. That completes the proof.